Have you ever wondered how a database can find one single record out of billions in what feels like an instant? I mean, it really does feel like magic, but it's not. Today, we're going to pull back the curtain and show you the secret behind this incredible speed. It all comes down to a data structure called the B-tree.
All right, so let's set the stage. Imagine you've got a table with a billion users. A billion! And your job is to find just one of them by their ID. You type in your query, you hit enter, and bam! The result is just there. It pops up before you can even blink. How on earth is that even possible?
Yeah, I mean, that's the big question, right? Because if you think about it, the obvious way, just scanning every single record one by one, that would take forever, literally. So there has to be a smarter way. And, well, there is. And the answer is, honestly, it's pretty mind-blowing.
That's right. Not millions of steps, not even thousands. For a table with a billion records, a well-designed database index can find the exact piece of data you need in, get this, just 3 or 4 steps. 3 or 4. So to understand how this is even possible, we first have to talk about the real enemy of speed in a database. You see, the problem isn't really about how many comparisons a computer has to make. Your CPU is ridiculously fast. It can chew through calculations like nobody's business. Now, the real bottleneck, the thing that grinds everything to a halt, is having to read data from storage, from the disk.
Think of it like this. Getting data from memory, from RAM, is like grabbing a book that's sitting right on your desk. It takes nanoseconds. But fetching data from a disk, even a super fast SSD, is like having to get up, walk out of your house, and go to the library down the street. It's just orders of magnitude slower. So the number one rule, the whole game, is this. We have to minimize the number of times we go to the disk. That's it.
Okay, so if you've taken any computer science classes, your brain is probably screaming, binary search tree right now, right? It's a classic data structure, the go-to for searching, but for this specific problem, it's actually the exact wrong tool for the job.
And here's why. A binary tree is like a really tall, skinny ladder. For a billion items, that ladder would be incredibly deep. We're talking something like 30 levels tall. Now, if every step on that ladder, every level you go down, could be another slow trip to the disk, well, that's 30 trips to the library. That is way, way too slow. We need a totally different shape.
So, if the tall, skinny ladder is the problem, what's the solution? Well, we need the opposite. We need something short and wide. We need a data structure that was built from the ground up to solve this disk problem. And that is where the B-tree comes in.
So what is a B-tree? Well, it's a type of self-balancing tree, sure, but its absolute defining feature, the thing that changes everything, is that each node in the tree can hold lots of keys, not just 1 or 2. And this seemingly simple change has massive implications for performance. And this is where our analogy gets an upgrade. Instead of that slow, step-by-step ladder, a B-tree is like a big, wide elevator. When we make that one slow trip to the disk, we're not just bringing back one measly key. No, we're bringing back a whole floor of information, an entire page or node that might contain hundreds, maybe even thousands of keys. So one trip to the disk gives us a ton of information to work with.
And this right here really just drives the point home. Take a look at the height for a billion items. A binary tree? It's about 30 levels deep. That's potentially 30 disk reads. But a B-tree? It's just 3 or 4 levels deep. That's a maximum of 4 disk reads to find anything. That is the magic trick right there.
So the secret ingredient here, the technical term for it, is fan-out. It's basically just the number of children each node can have. A binary tree, by definition, has a fan-out of 2. But a B-tree, its fan-out can be over 200. So every single node becomes this massive branching point, and that is exactly why the tree stays so ridiculously short.
And this gets us to the tiny bit of math behind the magic. You might remember that the height of a binary tree grows at log base 2 of n. Well, for a B-tree, it's log base times b of n, where that b is our huge fan-out number, like 200 or more. And when the base of your logarithm is that big, the tree height just grows incredibly slowly, even if you keep throwing millions and millions more items at it.
So, that's the B-tree in a nutshell. But in the real world, most modern databases actually use a clever evolution of it called the B+ tree. It takes the core idea and adds a couple of really important upgrades that make it even more perfect for what databases need to do.
Okay, so there are 2 main upgrades. First, in a B+ tree, only the leaf nodes, the nodes at the very bottom level of the tree, actually hold pointers to the data. All the other nodes above them are just for navigation, like a big roadmap. And second, all of those leaf nodes are connected to each other side by side in a linked list. Now that second point, that is a true game changer.
So why is having a linked list at the bottom so important? What's the big deal? Well, it makes one of the most common things you do with a database, scanning for a range of values, insanely fast.
I mean, think about a super common SQL query like this one. You're not looking for a single person, you're looking for everyone between a certain age. Without the right data structure, a query like this could be really painful and slow, but with a B+ tree, it's incredibly efficient.
So here's how it works. The database does that super fast B-tree search to find the start of the range. In our example, the person who was 25. But then, instead of having to go back up and down the tree for every single value, it just follows the linked list. It just scoots sideways from one leaf node to the next, collecting all the data it needs until it hits the end of the range. It's just one simple, fast scan right across the bottom level.
And really, this is the most important thing to remember. The B+ tree isn't just some clever algorithm in a textbook. It's a brilliant piece of engineering that is built specifically for the physical reality of how our hardware works. It's designed to deal with that massive speed gap between memory and disk. And by focusing on minimizing the absolute slowest part of the process, it delivers that incredible performance we see every day.
So, the next time you run a query and get a result back instantly from a massive database, you'll know the secret. It's not magic at all. It's just a very, very wide elevator. And it kind of makes you wonder, right? What other pieces of tech magic that we use every day are really just the result of a clever, perfectly chosen data structure?